Thank you. This morning we're going to have an exciting talk. Exciting because I think it opens the door to behavior analysis meeting a wider public. As we attempt to publish more widely than our familiar and beloved journals, we'll run against the questions of, well, was that difference significant? And we don't necessarily want to play their game of null hypothesis statistical testing, which is not a good game to play for a lot of reasons, for the questions that we ask. And so what are the alternatives? And fortunately, they're not that complicated to have an alternative approach to evaluating whether you've got a robust effect that deserves talking about as though you had an effect, and being able to make probability kinds of statements about it. All new math is a little bit scary, but once you start working through it, and the whole point of this, it's a tutorial. Chris, with the help of his colleague Derek, who couldn't be here, will make it easy for you to start playing this game. All statements about the world are model-based. Words, this is a lectern, that is a podium. Those are models. Definitions, reinforcement is a model. Equations are models. And then we have statistical models. There are probably a couple different things going on here, is what we want to be able to get some numbers associated with. Or this intervention was probably effective, or Jack McDowell's is probably the correct model, or not, as the case may be. So all statistical models involve comparison of two or more things. Before or after comparison, control experimental condition. We want to know how likely the differences reflect replicable. We can say real or we can say truth, but what we really mean is replicable. Now, that's about as good as we're going to do in contacting the Almighty. So we want to know how likely these things are going to replicate. So here you've got some data, stippled bars and clear bars, and you want to know, is the best way to talk about this one distribution with mean right around 7? Or is it okay or even better to talk about it as two distributions, with one a mean around 4 and the other around 10, let's say? How do you know? How do you know? Well, Chris will show you how you know. So you can do it with theoretical models as well, like the various versions of the matching law. We want to know what's the most consistent with the data. I don't like it when people say predict the data. We rarely do that, but we're looking for what model represents the data best. And so here's some data that you might think of as under-matching, perhaps. And a linear equation does just fine. A simple matching law does, well, generalized matching law does okay by them, but there's systematic deviation, and we know that that model is obviously doing better. Why shouldn't we choose it? Well, there's a question of generalizability. If you overfit a model, as I'm doing here, it's not likely to work in the future on a new data set. There's a trade-off between parsimony, fewer parameters, and precision, how closely you fit the data. That's really important. And unfortunately, until recently, there hadn't been a good way to think about that trade-off between parsimony and accuracy. And thanks to the work of a Japanese statistician, Akaike, Akaike, he found a way to take an approach that had been around, Kullback-Leibler, measuring the information theoretic distance between two distributions. That approach, you always really needed to know what the generating model was. And his approach was a brilliant way of sidestepping that and making this process general. So what Chris is going to talk to you about today is this brilliant insight that's been evolved ever since Akaike into the exact tool that we want for analyzing our data. So I'd like to have you welcome Chris while I change computers. Okay, thank you. We'll have some time for questions after. It's very important that you make notes to ask questions and you ask them and don't feel stupid about asking them. This is new math for some of you, and no question stupid in that context. Oops.
Well, thanks, Peter, for that, for setting this talk up very nicely. Is this working okay? For setting this talk up very nicely, setting up the basic issue that we're dealing with. What I want to talk about today is an approach that we've been taking, inspired really by Derek, that we've been taking in fitting models to data. I'll give you the background sources for this information at the end of the talk, but it's basically a book by Burnham and Anderson on it called Information Theoretic Approaches and Multi-Model Approaches. Derek unfortunately couldn't talk today. We were going to do a 1-2 punch here, but he was unable to attend. So my plan is to begin with a brief background about the replication crisis that all of us are familiar with, and the role that null hypothesis statistical testing may be playing in this crisis. I'll talk a bit about log likelihood because that's the basis for the Akaike Information Criteria, and I'll talk a little bit of Kullback-Leibler divergence and distance. But this is going to be a very practical how-to sort of thing. We're going to wave at theory, but mostly we're going to talk about how to approach this. And at the end, what we're going to do is test a bunch of models and ask, what is the probability that each model in this set of models is the best of the models that we're testing? And then I'll say a word about prediction based on multiple models and then some cautions. But first, the replication crisis. I think we all have read about this. A paper published by what's called the Open Science Collaboration. It was a large number of authors. It was published in 2015 in Science that described a failure to replicate a number of experiments in psychological science and top psychology journals, including Psychological Science, Journal of Personality and Social Psychology, and Journal of Experimental Psychology, Learning, Memory, and Cognition. They carefully selected the experiments to replicate. There were sequential experiments in 3 years, but mostly, not entirely, that were replicated by people who had the background and the expertise to do so. This is one of the figures from that paper. So this is a density plot showing, is this working? Yeah, showing the p-values, the p-values, the number of p-values from the original published papers. The dotted line shows p of 0.05. Not surprisingly, most of the p-values are less than 0.05 in these three papers. In these papers, there were 3 that were greater than 0.05. The width of this density plot shows the number of those. So this is in the original study. In the replications, though, you get a distribution that looks like this. Most of the p-values were greater than about 0.25 or so. And relatively few of the p-values were less than 0.05. So at the very least, a p-value of 0.05 did not do a good job of predicting the replication. And if you know what a p-value is about, then you won't be surprised. But we're going to talk about that in a moment anyway. This is not just a psychology problem. It's not just because we're a soft science or because behavior is so difficult to study. It's a problem that's being faced in other disciplines as well. This paper was published in Nature Review, Drug Discoveries, a few years ago. Bayer Health Care evaluated the reproducibility of drugs under development for oncology, for women's health, and for cardiovascular disease. These data came from cell lines, they came from in vitro assays, so under really tightly controlled conditions. And almost two-thirds of their results were not published in the open literature, and in another analysis, many of them were not replicated either in the in-house data. Only about 20, and these failures to replicate had financial consequences. It led to the termination of a number of projects. And this was the case even when there was a one-to-one attempt to replicate. So even when the conditions under which the results were obtained was replicated in what Sidman would call a direct replication. Why is this the case? Well, Regina Nuzzo published a paper in Nature in 2014 that looked at taking the Bayesian approach and said, okay, let's consider 3 types of studies. One would be a long shot, one would be equal odds, and one would be a likely bet. This is the long shot here. So by long shot, what we mean is a prior probability of 95% that there's no real effect. We do an experiment on something that is a long shot, and we get a p-value of 0.05. And what's the probability that there is no real effect? And it turns out with a p-value of 0.05, the probability in this long shot that there's no real effect is close to 90%. 0.01, it's close to 70%. What do we mean by a long shot? Well, this is the stuff that gets in the literature. I mean, these are the surprising things. These are the cool effects. If it's a toss-up, the situation gets a little bit better, a 30% chance of replicating a p-value of 0.05. If it's a good bet, if it's old stuff, if it's something that we're pretty sure about, the p-value does a good job of predicting the probability of replication. So one of the problems may be a misunderstanding and a misinterpretation of what the p-value is. Does the p-value really indicate the probability of a replication? No, it does not. And one of the reasons is that null hypothesis statistical testing tests the probability of the data given the null hypothesis. It tests the probability of the data given the null hypothesis. This is not the same as the probability of the null hypothesis given the data. And as Nuzo showed, plausibility is an important criteria. Mark Branch put it very nicely, and he used an example that I think is really pertinent today. But he pointed the usual tactic is to believe that if a particular set of data is unlikely to occur, if the null hypothesis is assumed, then one can conclude that the null hypothesis is probably untrue. Let me hasten to remind you, this is not the case, but this is what people commonly believe. Thus, if the probability of the data given the null hypothesis is small, then the probability of the null hypothesis given the data is small. But this is false. But taking this approach, and if you buy into this approach, you could probably prove that Barack Obama is not an American. And I wish I could claim this, but this is Mark Branch's example. The null hypothesis is that the next person that I meet is an American, then is unlikely to be Barack Obama. The next person I meet is Barack Obama. Therefore, Trump was right. Barack Obama is not an American. Alternatives have been suggested. Pre-registration of methods and data analytic strategies, reporting all tests, report effect sizes. Peter Killeen has suggested PREP, which does a nice job of blending signal detection theory with null hypothesis statistical testing to come up with a probability of replication. But I'm going to talk about another approach, which is based on log likelihood, and is called information theoretic approaches. And it addresses the question of what it is that we want to know. We want to know the empirical evidence for hypothesis J relative to all the others in the set. Null hypothesis testing does not answer this question. And in fact, significant tests can never be for an hypothesis. And as a result, you cannot build a cumulative science by rejecting null hypotheses. So I'm going to do a very brief introduction to log likelihood just to give you a sense of what this is about, because it's the basis for what follows. So we'll examine a very simple case of log likelihood. We'll estimate the likelihood of a single parameter, and then later we'll talk about the estimation of a model. So let's consider what probability class is love, and that is a coin toss. We flip a coin. We hypothesize that the coin is a fair coin. We flip it 50 times, and we obtain 10 heads. We want to know the probability of obtaining 10 heads in 50 trials with an assumed honest coin. We do math stuff, and we come up with a p of 0.0000.12, and actually that doesn't accumulate more extreme outcomes. But so we reject the null hypothesis of an honest coin. But all that we know is that the coin is biased. If we took a log likelihood approach, the log likelihood approach is a very different approach, and it considers a different problem. Now we want to know what are the likely values of p given that you've got 10 successes. What are the likely values of p given that you've got 10 successes in 50 trials? So p now becomes a variable. And so we vary p, and we find the likelihood that p is 0.2 in 10 out of 50, and the likelihood that it's 0.4, and the likelihood that it's 0.1, and we generate a distribution of p values, and we see that the maximum likelihood occurs with a probability of heads of 0.2. So what we have here now is the probability of a parameter given the data. This example illustrates the estimation of a parameter. We would really like to test a collection of models, and we need a metric for selecting the best one. Thus, we must test multiple models. Note here that null hypothesis testing discourages testing multiple models. The information theoretic approach encourages the testing of multiple models, at least up to a point. So we're talking about model selection. So where we're headed is we're going to generate a data set that could come from a delayed discounting experiment. The data set that we're going to generate is truth. We know what the parameters are, we know what the equation was that entered into this. We're going to fit a collection of models to the obtained data and ask which model in this pool is the most likely to give the data collected. And then we're going to show, and in the process we're going to show that it doesn't matter what truth is. So, simple example, delayed discounting. I'll go through this very quickly. Consider a rodenttoid sort of creature in a delayed discounting experiment asking to select between a smaller sooner reinforcer, 1 drop of milk, and a larger later reinforcer, 4 drops of milk after a varied delay. So the mouse is presented with 2 levers, and sometimes he selects the smaller one, and sometimes he selects the larger one, and we would get a delayed discounting function that looks something like this. So as the delay increases, the probability of selecting the larger later reinforcer decreases. I generated these data using an hyperboloid function that's shown here with a discounting rate of 0.4 and an exponent here of 0.5, which flattens out this curve a little bit. So we call this hyperboloid model. This is truth. This is the model that we are going, and these are the data, the points there are the data that we're going to try to fit. Where we're headed, we're going to build this god-awful looking table, but we're going to do it piece by piece. But this table consists of a collection of models, hyperboloid models, exponential, linear, and mean. We're going to calculate Akaike Information Criteria, AICC, Akaike Information Criteria, and correct it for small samples, which is generally recommended for most experiments. We're going to rank order these AICCs with the smallest at the top, and these are negative numbers for this particular case. So this is minus 66.2. It's the smallest of these. We're going to rank order these. We're going to subtract all of the different AICCs from the best one. This is going to give us an Akaike weight, which will be interpreted as the probability that each of these models is the best in the set, and we're going to compare this with R squared. Okay, so that's where we're headed. And if you got that table, we can all go home now. So, but let's back up for a moment and talk about the goals of modeling. And we're going to talk about 2 of them. One is to come up with a quantitative estimate of the rate of discounting. I'm sorry, but one is to determine the structure of choice. What does choice in this setting look like? Is it exponential? Is it linear? Is it hyperbolic? Is it hyperboloid? And that has, the model itself has important theoretical implications. So this is about the theory of behavior under this procedure. But another is to come up with a quantitative estimate of the rate of discounting. And this quantitative estimate can be used to determine the impact of some kind of a challenge, like a drug or a neurotoxic substance, or environmental stressor, or age, or what have you. These are different goals. We'll emphasize the first, and we'll comment on how the models can be combined to accomplish the second. And we'll test a number of models. So we'll test some models that are called nested models, beginning with a full model. Y equals an intercept up here at the top, divided by 1 plus kx, with k is the discounting parameter, raised to an exponent. We'll talk about hyperboloid without the y0, so we'll force an intercept. We'll talk about hyperbolic without an intercept, and we'll talk about hyperbolic with no intercept. All of these are nested under the full model here. But with this approach, you can also, as long as you're working with the same data set, this is really key, as long as you're working with the same data set, you can test on different types of models as well and include them in the list. So we'll begin with a really stupid model, the mean. We'll work up to linear and exponential. So we begin with a grand mean. This might even be viewed as a null hypothesis. So we have our data here. The red line shows how we're modeling the data. And what we're saying is the best model for this data is the grand mean. So whatever the delay, the the probability of the larger reinforcer is going to be 0.51. The difference between the real model and the noise can be quantified. At x equals 0, this distance is large. At x equals 8, this distance, this divergence between the data and the model is small. And at x equals 16, it is large. Okay? So, in a sense, what we're doing is building residuals. Everybody understands residuals. And what we'll see is that the information material actually also builds on residuals. But there's another way of interpreting this. The distance illustrated by the bars is also the surprise value of the obtained data point. So if we estimate that the mean, if we think that if we model this as the mean, 0.51, we run the experiment at a 0-second delay and we get a value of 0.995 or whatever that is, then we're surprised. That's a surprising data point. And that surprise contains information. If we run it at 8 seconds, we're not very surprised by the outcome, but again, out here at the longer delay, we would be surprised by the outcome. So, because these are low probability events. Okay, so that's the mean. Now we try a different model, a linear model. We simply fit a straight line to these data. The divergence between the model and reality are smaller. We're, in a sense, going to be accumulating these divergences to come up with a total surprise value for the model, the information content in the model. But the distances between the model and reality are smaller, as are the surprises. And so this is where the Kovac-Leibler information distance business comes in. In the real world, y is not hyperboloid. That's truth. We've estimated two models, the mean and we're linear. And so there's information in reality, there's information in the mean, and there's information content in the linear model. What's the distance between these models, the mean and linear, and truth? The units here are in KL information units for Kovac-Leibler. And so, at least to a southern ear, KL information sounds an awful lot like a leafy plant. So I'm proposing that we use KL units to measure our disparity between the model and the our leafy vegetable and the distance. Or alternatively, and this makes contact with the surprise business, what is the information lost by fitting a model to the data? So how much information are we losing by modeling reality? Because as Peter said, no model is perfect and no model is truth. So we compare these two models, the mean and the linear estimate. We've got a residual sum of squares for each one, and now we can compute the log likelihood using math. And I won't walk through this other than to point out that it is related to the residual sum of squares divided by the degree of freedom, so it's related to the variance in the model. And this at least is true for least squares regression and normally distributed errors. Okay. An important component here is K, which is the number of estimable parameters, and K is a little bit different here for the degrees of freedom that you all are familiar with. And it would be used as a penalty when we calculate the AICC. So for the mean model, K, the number of estimable parameters, is 2. One for the mean, and then another for the variance. And this is something that trips people up a lot when doing this approach. You've got to throw in a parameter because you're estimating the variance here. For the linear model, K is 3. Intercept, slope, and again, the variance. And in fact, if you don't have an intercept included in the model, you've got to throw in a K for the intercept as well. The AICC then can be calculated from the log likelihood, which in turn is determined from the residual sum of squares, plus 2 times K, so here's our penalty, plus a correction factor for the small sample size. We'll see the equation for the correction factor in just a moment, but we'll just leave it as a correction factor in just a moment. We order these two from smallest to largest, and we come up with a delta AICC, which is just the difference in the AICC of the best model. So the best model, the difference of course is 0, because it is that model. And for the mean, that difference is 16.3. This gets us to Yeah, okay. So this gets us to an evidence ratio, which is calculated from E, the natural log, E to the delta I, which is the difference, the delta AICC, divided by 2. So for the linear model, the best model is E to the 0, which is 1. So the probability, so the evidence that the best model is the best model is 1. For the mean, and this can be viewed as an odds against, or an odds in favor. So for the mean, the odds against the mean being the best model, or the better model here, is 0.000765. We can take the inverse of this and say that 3,463 to 1 check. This is a worse model. Remember this number, 3,463. Okay, so how do we think of these AICC differences? Well, I do this example because when you get into this, you'll find out that sometimes you can get AICCs that are huge. So we're looking at differences sometimes, differences in this case of, say, 14, but the AICC can be 5,000. And when you first get into this, it looks like you've got a difference of 5 with an AICC of 5,000. How do we interpret that? It doesn't sound like much. Well, we can think of this as comparing the height of 2 people standing on the shore. Elevation 0. One head, the adult, height is 6 feet above sea level. The other, the child, height is 3 feet above sea level. The difference there is 3 feet. If that parent and child move to Denver, go for a hike, and we now test the elevation above sea level. It's a mile plus 6 feet and a mile plus 3 feet. But the difference in height remains the same. And it's the difference in height, it's the difference in AICC that is the important variable here. So where are we? We've generated a true known discounting function. We've hypothesized that a model was a mean, then estimated the divergence from reality. We next hypothesized that the model was a linear function, did the same estimate. Notice that when we did this, there was no truth in there. The true model, the actual model, wasn't involved in any of these estimates with their truth, right? In Burnham and Anderson's classic, wonderful phrase, truth drops out as a constant. So here we have the equation for KL information. I'm not going to do the tedious thing of walking through the entire equation, but I'll just point out a couple of elements of it. So this value on the left is the KL, or the number of kale plants, distance from truth, and it is captured in this equation here, which is the information content in truth minus the information content in the estimate. So the information lost is the information in truth minus the information estimate. So first we model reality P with one model, pi 1. Next we consider another model, pi 2, and we compare them. So the information loss using model 1 minus the information loss using model 2 is truth minus estimate 1 minus truth minus estimate 2. Truth is a constant. It never changes, right? So we get truth minus truth plus estimate 2 minus estimate 1, and truth drops out. So wither truth? Well, truth withers. So truth drops out, and we don't really care about it. All we care is which of the models is best at fitting these data, or which model minimizes the information lost. So now we try an exponential fit. The red line shows the exponential fit. The equation is here. This is a better fit, but there's still some disparity at the extremes. We now add the exponential to this table. And again, we have a log likelihood from the table, and this can be obtained in several ways, including computer output. The K for the exponential is the same as it is for the linear. We have a new AICC because we have a new residual sum of squares and a new log likelihood. And so the AICCs have not changed here. But what has changed is the lining up of the models and the delta AICCs. Because now we have a better model up here at the top. And so we subtract the linear from the best one now. And so the linear, instead of having a delta AIC of 0, is now a delta AICC of 7.9. So it's changed. And for the mean, it too has changed. So the likelihood, the evidence ratios for these models then will be, the odds against is quite different. So the odds against the mean being the linear being the best model now are 0.019, and the odds against for the mean have increased to 67,000 from about 3,400, which is what we had before. So when we have, as we add better models to our table, as we add better models to be compared, then we get better estimates and are more likely to find the best model here. Okay, so interpreting AICC differences. This is a rule of thumb. This is a rule of thumb. And certainly not a guideline. And the one thing you do want to avoid here is coming up with a bright line like 0.05. What this information does is provide to the investigator, provides to the scientist some guidelines of how to interpret the different models that he's testing. Okay? So if the AICC is about 0 to 2, then evidence level of support is substantial. 4 to 7, considerably less. Greater than 10, the model is implausible. Okay? So AICC can be used to compare models, it tells us which produces the least loss of information, or which is closest in our KL units to truth. Another way, so we can look at it this way. We have truth down here at the bottom. We don't know what the AICC of it is. It can be any constant that we want. We'll call it 100 just because it makes subtractions convenient. And so our exponential model is this distance from truth, minus 45. Linear is this distance from truth, minus 52 KL units. Mean is this distance from truth, minus 67. Again, we don't know what truth is. It's just, we're calling it some constant. But what's important here, I thought I'd animate this, what's important here is really how these models line up compared with each other. Once again, truth withers away. Now, a quick word about the AIC. This is an ingenious proof that links KL information, which I've just talked about, to statistical theory using the Akaike Information Criteria. So roughly, it is the expected value of KL information, which is the log likelihood of the model given the data minus K, this parameter. And he subtracted K because his proof showed a bias that was, in his words, at least English translation, very close to the number of parameters in the model. Okay. So, I haven't talked about this column here, so I'm going to introduce this one now. This is the Akaike weight. What we're doing to get this is using this equation down here in the bottom left. We are summing up all of these evidence ratios, and we're creating a denominator. We're summing up the evidence ratios, that's the denominator, and then we divide the evidence ratio for the exponential by that denominator, the linear by that denominator, and the mean by that denominator. So this is a sort of a proportion. And the Akaike weight then for the exponential is 0.998, for the linear is 0.02, and with rounding for the mean is 0. These add up to 1, which is nice because this Akaike weight is interpreted as a probability. So for the mean, just to walk through the calculations, 0.02 divided by 1 plus 0.02 plus a very small number. The Akaike weight is a probability. It is also interpreted as the Bayesian probability with judiciously selected priors. So this is sort of a sideways entry into Bayesian approaches. And it certainly puts this approach in touch with the information that can come from the Bayesian analysis. This Akaike weight can also be used to weight each model in building a composite model. So if we were to build a composite model, we would multiply the parameters from the exponential by 0.98, the parameters from the linear by 0.02, and 0 times the mean, and come up with a composite weighted model that does a slightly better job of fitting the data. So we've tested 3 of the unnested models. I'm not going to go very quickly through some nested models. This is hyperboloid data fit with a hyperbolic function. Does a pretty good job. Again, some divergence here at the extremes. Hyperboloid data fitted with, let's see, hyperboloid model does a very nice job. In both of these cases, we're forcing the intercept to be 1.0, but we notice that actually the intercept is a little bit less than 1.0, so we might want to try a couple models and let the intercept vary. So we do that for both the hyperbolic and the hyperboloid model. We fit the intercept, and we come up with these two fits, which seems to be even provide a little bit of improvement. And so now we build our table more. To simplify things just marginally, I've dropped the mean out from the bottom. So, so let's walk through what this is telling us. We have 6 different models here. We have our AICCs. Notice we've got a K of 4 here for the hyperboloid plus the intercept, because we've added the intercept, plus the exponent. We've got our AICCs. We rank order the AICCs. We have our rank order that we calculate our changes, our differences in AICC, and we come up with evidence ratios, which are listed there. I won't walk us through it. I'll focus instead on the Akaike weight. And what we see here is that it'd be hard to pick between the hyperboloid and the hyperboloid with an intercept. Each of these is approximately equally likely. So what does that mean? So we're not rejecting or accepting hypotheses here. What the investigator can look at and say, we need more data. We need better experiments. From what we know, these two are roughly equivalent models. We can't pick between the two without further work. This is important information, and a lot more important than just saying the null hypothesis, which in this case would be the mean, is false. And I've rerun this, this was with 11 data points, I've rerun this with 110 data points, and you can distinguish between these two with a larger data set. Now, the other thing that I want to point out here is R squared. These are pseudo R squared. You're not supposed to do this, but people do it, so I've done it. And notice here, I put this here because if we were to try to decide which is the best model based on the R squared, we'd have a difficult time, because these R squared are all greater than 0.89, all greater than 0.89. But if we focus on the Akaike weights, we have 2 models that are clearly at the top. Another one, hyperbolic plus the intercept, somewhat plausible, but 0.06 chance, and the pure hyperbolic for these data anyway, a 0.01 chance of being. So odds are 100 to 1 against this being the best model here. This is enormous information, and again, it's better than the, and you feel more confident about this than you do from the R squared. Multi-model inference. Akaike weights provide a way to combine models. So prediction can be improved by combining plausible models after weighting by W sub I. So, for example, the multiple terms, so we would weight the hyperboloid by 0.5, the plus intercept by 0.5, the hyperboloid by 0.43, and so on down the line to sharpen the prediction if our interest were in predicting the a particular parameter, the indifference point, say, or something like that. Now, there's some precautions that need to be added. First, all the models need to be based on the same data set. This is absolutely crucial. If not, then what you're doing is comparing the height of a child standing at the shore with the height of an adult standing in Denver, and you get something very strange. You cannot replace, this does not replace thoughtful questions. You can't just go in and whimsically add models. It's always a good idea to have some theoretical basis for the models that you're testing. Another is that the true model is not in the set. Remember, truth drops out at a constant. We can just say, of the models that we tested, this is the best one, which is why it's important to test a collection of models. It's not a statistical test, it's evidence, but still, post hoc examination should be, is okay, it's perfectly acceptable, but it should be identified as such. You may go into this data set and say, oh, I don't know, maybe we should add a term for the intercept. Now, in a sense, that was post hoc. And it certainly should be identified as such, it's hypothesis generating, it's fine, but go ahead and do it. Be sure to include the right number of estimable parameters, and I'll just wrap up by pointing out, if you're interested in this, I'll point out 2 excellent sources, and it really forms the basis for this talk. One is a primer, which is on the right, by David Anderson, model-based inference. Actually, I have a copy of it up here if you want to leaf through it. He does a very good job. It's a good narrative of the thinking behind this approach, how to implement it, and how to implement it. The one on the left is by Kenneth Burnham and David Anderson, and it provides a lot more detail as well as some proofs in the appendices. So, thank you, and I think we have time for a few questions.